One of the characteristics of the synchronous grid, which we discussed in the previous lecture, was the fact that the synchronous generators which are interconnected in a synchronous grid by AC lines tend to stay in synchronism, and if you give in fact a disturbance, they tend to swing. That is, there is a relative motion between them, which we hope, which is in fact oscillatory, because the synchronous machines connected by AC lines can be considered analogous to masses connected by springs. You find that there is an oscillatory behavior, and if the oscillation in fact damps out, there are mechanisms of damping. In fact, the damper windings and the field winding of a synchronous machine in fact help in damping out these oscillations. You will find that once the oscillations die out, the machines stay in synchronism. So, if you give a disturbance, you typically see a swing, which eventually, if everything is fine, it will die out, and the machines will stay in synchronism. In fact, so the inherent equations of the synchronous machine, the motion of a synchronous machine and the characteristics of AC transmission lines, which are dependent on the phase angular difference between the voltage at both ends, in fact ensure that the machines tend to stay in synchronism. Of course, there are exceptions to this. The thing is that in case you give a large disturbance to machines which are in synchronism, you may actually because of the disturbance, the machines may transiently have speeds and angular deviations between each of them which are very large, and in that case the AC transmission lines do not provide the restorative torques to bring back the machines into synchronism. It's much like a railway engine on a track, and normally it does remain on the track because of the nature of the rails and the shape of the wheels, but if you give a big disturbance, a train may get derailed. So, something of the similar kind happens. You do not have to, in fact, the inherent equations of synchronous machines connected to each other by AC transmission lines, these itself ensure that the machines stay in synchronism, but for large disturbances you may actually lose synchronism. The main reason for this is that the restorative torques caused by the AC power angle characteristic is a nonlinear function of the phase angular difference. So, in case the phase angular difference is larger, the restorative torques actually start reducing and may even become negative. So, you may actually have the synchronous machine pushed away from each other even though they are connected by the AC transmission lines. So, you may actually have a loss of synchronism of machines which are connected to each other by AC transmission lines if you give a large enough disturbance. What are the large disturbances? Typically faults or multiple faults which occur in a system, and line trippings may actually cause machines to go out of step, and this has in fact been observed in the Indian grid and in grids around the world. So, a lot of effort is in fact invested in trying to ensure that the for all credible disturbances which may occur or likely to occur, the machines will stay in synchronism. Now, another point which I must also bring out here is this another manifestation of instability in synchronous grids relating to the motion of the rotors, and that really is what is known as unstable power swings. Power swings are seen after a disturbance, even when you have got small disturbances, and although the machine may not lose synchronism outright as is seen in this figure here, it may actually have undamped oscillations which may in fact remain sustained for quite some time, or in fact they may even grow with time. The another thing which we saw in the previous lecture was in addition to this, in a synchronous grid, in addition to this, there is also a question of how the center of motion inertia of the system behaves, and the center of inertia motion is dictated in fact by the total load generation balance, and the total load generation balance in fact has to be come to an equilibrium. That is, the total load should be equal to the total generation, of course, and also the generation to account for the losses which take place in the system. And once that equilibrium is reached, if it is reached at a certain frequency, the system will settle to that frequency. So, if you are already operating at a given frequency and there is a load tripping, then the generator speeds will go to a new equilibrium depending on how the governors in the generating systems react. Now, remember that eventually in a synchronous grid there is only one frequency in steady state if you are stable. So, if you are stable, all machines are in synchronism, and if they are in synchronism, that means the frequency everywhere is the same. The governors effectively are trying to regulate the frequency, but there are many governors and many generators, and they are locally trying to regulate the frequency. Now, the question then arises is if how do these generators share their responsibility of regulating the frequency. For example, if there is a sudden generation trip, there is suddenly a load generation imbalance, the load is more than the generation because of the one generator trips. Initially, let us say we are operating at equilibrium. In that case, you will find that the frequency dips, and the governors will see this dip in the frequency and try to increase the mechanical power. Now, this happens in all generators in which the governor is active and there is margin to increase the power. And what I mean is that the generator can increase power and still stay within its rating. So, suppose there are many such generators, then all of them will react. So, to what extent will they react will of course depend on the gains, or the what is known as the reciprocal of the gains are called the droops of the governor. So, if a generator has a larger gain in its governor, then you find that it may take on more load. In fact, this the gain, the reciprocal, as I said, of the gain is called the droop, and 5% droop means that the gain is 20, but the gain remember here is in per unit. It is in fact scaled with respect to the generator power. So, if two generators have 5% droop, but their ratings are different, their actual gains actually are different. Okay. So, for example, 20% droop of a 500 megawatt generator is twice will yield twice the gain as in a 250 megawatt generator with the same droop. So, what you really see is that so the main thing is the gain of the governor. Usually the governors are do local control of the frequency, but eventually frequency everywhere is going to be the same if you are stable. So, every generator in fact contributes a little bit of power to ensure frequency balance, and the share of that power depends on the droop. Now, if any generator has got very large gain or infinite gain, steady state gain, it will in fact take on the entire responsibility of maintaining the frequency. So, if you have got a generator with a droop, with a gain in the governor or the reciprocal of the droop being near infinity at in the steady state conditions, it will take on the entire it will take the entire responsibility in steady state of maintaining the frequency. Such governors are called isochronous governors. Now, so if you have got, for example, a PI controller instead of a proportional controller in a governing system, then the steady state error is 0, and the governor has infinite gain. So, you will find in fact that governor takes on the entire responsibility of maintaining the frequency, and the steady state error in the frequency after the governor has acted will be 0. So, the governor will force the system to reach the set point. Okay. So, such governors are special, they are called isochronous governors, but they are not usually, this is not a common practice, because you would rather have a large number of generators share the responsibility of maintaining the frequency, share rather contribute to little bit of power. For example, here in the second figure here, there is a load becomes more than the generation. So, the remaining generators in the system after this generator trip will all act in proportion to their the reciprocal of their droops. So, this is essentially how this responsibility is shared. Of course, depending on the gain, the final settling frequency is decided. Okay. So, this is essentially how the frequency is maintained stable. These two phenomena here correspond to relative angle stability. Okay. Okay, this is the stability of relative motion between generators. So, these are very characteristic things of synchronous grids. Okay. Yeah. Now, when you come to how machines, in fact, it is like a multi-mass, multi-spring system. When you have got when you have got a large number of machines connected to each other, and you will in fact find that machines, there are many modes of oscillations which are present. One can do a formal study of this using linear models, linearized models of a power system, and actually compute eigenvalues and eigenvectors, but that is not what we will do here. I just want to give you an intuitive kind of idea of how the behavior will be. So, the electromechanical behavior, the relative rotor motion, you will be characterized by many swing modes in a multi-machine system. So, they are characterized as inter-area modes, where large number of machines swing against another group of large group of machines. You may have machines within a power plant oscillating with respect to each other, or even local modes. These are all modes which are excited once you give a disturbance. Okay. Now, to just give you a picture of this, you can see in the next slide a disturbance, where you see this is in fact generator trip, the frequencies at various places in the grid after a generator trip at one power station in our country. And you will find that actually these are the swings, these are relative motion between the generators, and there is also a center of inertia motion which is in fact following, because there is a temporary load generation imbalance which is created when the generator trips when operating at this equilibrium. You will find of course many oscillations. In fact, there seems to be a superposition of various you can actually see quite distinctly that there is one slightly higher frequency mode, and also you will find that there is a relatively lower frequency mode also seen. So, this kind of behavior is in fact seen when you give a disturbance in a synchronous grid. Yeah. Sometimes these oscillations can also become unstable. In fact, you may find this is usually due to some control systems, feedback control systems, which inadvertently, means unintentionally, in fact cause the oscillations to grow. This is because of closed loop feedback control. Closed loop feedback control has to be designed very carefully, otherwise you may end up destabilizing some swing mode. So, this is also a well known phenomenon which occurs in synchronous grids. This is also an interesting measurement which is taken in our grid. This corresponds to the swing which is seen during synchronization. So, in fact, you find that this particular disturbance was in fact measured when the southern region of our country was synchronized, that is connected by an AC path to the rest of the country. And the one of the measurements here is of course from South India, and when this you find that the frequencies of both grids are different slightly, maybe 0.0, slightly less, around 0.025 hertz, and at this point they are synchronized. So, once they are synchronized, that is connected to each other by an AC line, you find that the frequencies merge in some ways. Of course, you see a swing which is very characteristic once you have got machines, very characteristic transient when you have got synchronous grids. Now, this brings us to an interesting point, that when you are connecting a synchronous source to an existing grid, you need to do it a bit gracefully. So, you need to connect your source to the grid in a very graceful way. This process is called synchronization. If you go to a power plant, there are special measures taken to when you want to connect your synchronous generator to the grid, you will actually have to start it up, get it to the frequency nearly equal to the frequency of the grid which is existing, and the existing frequency of the grid at that point of time, and ensure that the voltages of the grid at the point where you are going to connect are almost the same as the voltages of the synchronous machine which you are trying to interconnect to the grid. So, actually at the point where you connect the two machines to the machine to the grid, it is best you get a minimal transient if the frequencies of both the synchronous generator and the grid are practically equal. the phase angle as well as the magnitude of the voltages as well as the phase sequences match. So, when you connect the machines to the machine to the grid under these circumstances, it will gracefully latch on to the grid, and thereafter it stays in synchronism. Okay. So, it is like you have to do this very carefully, and you have in fact setups in the power plants which are called synchroscopes, which allow you to connect the two machines, rather connect the machine to the grid when the machine's voltage, frequency, phase angle etc. Match the voltage, frequency and the phase angle at the point of connection. So, when you connect it, there is a minimal current flow and the machine kind of locks on to the grid. So, this is in fact a similar manifestation, but on a very large scale. A whole entire grid, the southern grid of India is synchronized to the northern grid by connecting an AC line between them. So, this is a very interesting transient which you see. As I mentioned, you may actually have unstable swings. I had in fact shown you one example of that. This particular disturbance also shows you the growth of a swing. In fact, this is more or less like a gradual increase in swings. This is because of a control system instability. You find that because of the feedback control, you find that within a plant the power swing is increasing. This does not happen always. In fact, you can have such kind of instabilities if your control system is designed wrongly. In this case, a particular gain in the controller was in fact chosen with the wrong sign, and therefore, you found that the oscillation started increasing. So, this is incidental, this does not occur always, but it can happen. So, this is another phenomenon in the synchronous grid which can take place. In fact, if you are having this kind of unstable power swings, which is also called small signal instability, because these kind of unstable power swings may be excited even by small disturbances. You may actually, the oscillations may actually grow and cause a out of step operation. Eventually we lose synchronism because the oscillations will grow, and stretches in the spring, so to speak, will go on increasing, and beyond a point the springs will lose their restorative ability and you may lose synchronism. And you may also have a sometimes sustained large oscillation. So, both the things can occur, and in fact, just to show you this, this kind of thing has occurred in the past, where the oscillations have actually become unstable and blown up. Okay. So, these kind of phenomena do occur in a synchronous grid, and they have to be actually controlled. How do you damp the power swings? Well, by making changes in the control system. So, you can in fact alter the control system in, for example, the excitation system of a generator, or you can in fact modulate the power flow in an HVDC link in a certain manner, so as to damp out these power swings. So, these kind of controllers are called stabilizing controllers, and they are present in the controllable devices in the grid, like the generator excitation system, the HVDC links. If you have got STATCOMs and so on, you can actually modulate them. Usually power electronic controllers have a large bandwidth, that is they respond very fast. So, you can actually modulate, or you can modulate the set point and actually try to damp out these power swings. So, this is what is commonly done in most power systems. This is another example, we can move on. Remember that in synchronous grids, the problem of angular stability, this is just to reiterate, you have oscillatory behavior which depends on the operating condition, and this oscillation is always seen, but it is a problem only if it does not die out. If you give large disturbances, which is also called transient instability, this can actually cause transmission lines to lose their ability to pull the synchronous machines back into synchronism, because of the fact that the power flow versus the phase angular difference, the characteristic is non-linear. Okay. Now, interestingly, you can operate a system if it is potentially large disturbance unstable, because that depends on whether a disturbance will occur or not. Whereas, if you are a small disturbance unstable, eventually the oscillation will show up in some way or the other. Okay. So, small signal disturbance, you immediately have to try to have corrective measures like changing the operating point or adjusting the gains of your controllers, whereas large disturbance stability requires you to actually strengthen the system in some way. Okay. Strengthen, I mean, you need to make sure that your restorative ability of your transmission system should be high. One of the ways of doing it is actually to make our transmission system stronger, that is its restorative forces which are inversely proportional to the series reactance of the line. Power flow is inversely proportional to the reactances of the series reactance of the transmission lines. That series reactance should be reduced. So, one of the ways of course is to have series compensation of the reactance of a transmission line using capacitors. So, we have got series compensation of lines. Another way you can improve the stability, large disturbance stability, which is transient stability, is to try to operate at a slightly conservative way. That is, you keep the initial power flow through most of the transmission paths a bit conservatively low, so that there is enough margin for the spring to stretch. So that is one of the ways you can also improve transient stability, but that would mean that you need to alter the load and generation pattern in the system, which is not always easy to do, and there are economic consequences of doing that. In fact, one more way of improving a large system stability is use some of the equipment which can be controlled fast, like for example, the excitation system or HVDC links usually have a transient overrating, and you could in fact transiently increase the power through an HVDC link for a very short time, 5 seconds or 10 seconds, and that kind of control sometimes is just what is necessary to prevent an unstable situation from developing. So, this is the third way you can also improve your large disturbance stability. Yeah. Now, so this was the kind of behaviors we are talking of is in fact seen in synchronous grids. So, there are two kinds of behavior which are related to the electromechanical system of synchronous machines, that is frequency stability and angular stability. Angular stability itself has two manifestations. One, for large disturbances the machines may outright lose synchronism, and sometimes because of the control systems which are present, you may have the oscillations which are seen after any disturbance, they do not damp out. So, these two manifestations of stability are seen in large synchronous grids as well as small synchronous grids. But what if you have got asynchronous links? Now, one of the important things about HVDC links, that is you have got high voltage DC links, the picture which is shown here in fact has a line commutated converter based HVDC link, but it could be any even a voltage source converter based HVDC link. And the important thing is power flow is not inherently a function of the phase angular difference. Okay. So, the power flow in fact can be controlled. What is the power flow dependent on? Well, it depends on the voltage difference between this side and this side. In fact, depending on the voltage difference, the current will flow, and the DC current in fact will be dependent on the voltage difference at the two ends of the HVDC link and the resistance of the line which is there, line or reactor which is there, and this in fact flow is dependent on the voltage, and the voltage in fact can be controlled by controlling the firing angle of these converters. So, irrespective of what the frequency or even the phase angle of these two ends is, the DC voltage is can be controlled by in fact the firing angle of these converters. And because you can do that, the thing is that the power flow is not inherently a function of phase angular difference. And if your power flow is not a function of phase angular difference, it is very easy, there is nothing wrong, and very happily the two systems which are connected here can be at different frequencies. After all, you are rectifying it, and the rectified voltage is DC, and the flow through this is again DC current. So, it does not matter what the frequency here and here is, and very happily you can have transfer of power between these two systems or two generators through the HVDC link, and both the generators can be happily operating at different frequencies. This is not the case in case of an AC link. In an AC link, if two voltage sources are connected by an AC line with and they are at different frequencies, the power flow voltages etc., will fluctuate very wildly, and you are in fact in a kind of an unstable situation and you can't operate that way. On the other hand, here in a synchronous link you can operate that way, you can have two systems absolutely the frequencies could be independent. An interesting thought here of course is I did mention that power flows are not inherently a function of phase angular difference. The question which I can ask you is can you make power flow a function of the phase angular difference? The answer is yes. In fact, if I can regulate the power flow by controlling the firing angles of these two converters. So, in fact I could you know, I am not saying I will do it or it's a reasonable thing to do. It is not a reasonable thing to do probably. What you need to do is you could in fact measure the voltage here and the voltage here, and with today's global positioning satellite systems, you can actually accurately you know compute the phase angular difference between the two waveforms, because you can have a common time synchronized reference, and because you can measure the phase angular difference, you can make power flow a function of frequency by modulating the firing angle of the converters to be a function of the phase angular difference, the measured phase angular difference. But I will reiterate here, this is if I contrive to do it, that is if I do it on purpose, but inherently the power in fact can be kept a constant or it need not be modulated in this way. Okay. But this is an interesting thought that you can actually measure the phase angular difference at the two ends and actually modulate the power flow in a DC link, and in fact make the power flow a function of the phase angular difference by on purpose. Okay. And that would make the, you can make the HVDC link kind of mimic an AC transmission line. But why would you do that? So, you know, this is just a kind of interesting thought, it is not that it is something which ought to be done. So, we get back. So, the truth is that the HVDC link power flow is actually a function of how you control the converter, it is not a function of the phase angular difference inherently, and therefore, you can avoid problems of loss of synchronism etc. You can in fact regulate the power flow can be controlled by controlling the firing angle of the thyristors, frequency of the AC systems on both sides could be different. Okay. So, there are two things which can be achieved, frequency can be different, so there is no problem of stability, relative angle stability between these two grids. Within the two grids of course, you have the same you know, if this side is a synchronous grid and this side is synchronous, within those two synchronous grids of course, you will have frequency and angular stability problems, you could have. But between these systems they need not, there are no question of having swings etc., if the power flow is regulated and independent of the phase angular difference. So, one of the another thing which is important is that power flow can be regulated between the two systems. So, you can in fact keep the power at the contracted value between the two systems. That is, if two systems decide that this much is the power I would like to you know exchange, that is I want only 200 megawatts from your system, you could actually regulate that power flow and ensure only that much power is being sent and keep it constant at that value. Of course, having a controllable system like an HVDC link, it would probably be a bit foolish not to use its dynamic capability. There are of course power electronic converters which can actually help the system. So, for example, if this system is badly in need of some power, this guy could help him out by slightly changing the contracted amount of power. So, this kind of things can be done by an HVDC link. Power flow to the link is completely controlled and locally controlled. When you have got an AC system, for example, a meshed AC system, the power flows in each transmission path actually are dependent on the reactances of the path, where the loads are and where the generation is. So, in fact, power flow is not in each transmission path is difficult to control in an AC transmission system. On the other hand, in a HVDC link, you can control the power flow locally. Yeah. So, usually if you have got, for example, a system like this, you have got area 1 and area 2 and they are connected by two AC lines. And if that is the case, and suppose uh, the area 1 has a generation of 1000 megawatt and has a load of 500 megawatt. Okay, let us assume it is lossless, it is a lossless system just for the sake of this example. And let us say here the generation is 1000 500 and the load is 1000 megawatt. Then the power flow in these two lines will have to be 500 megawatt. So, in fact, you can't do anything in these in the suppose these are AC transmission lines, then the total power flow P1 plus P2 in the two transmission lines will be equal to 500. There is very little you can do in the AC transmission lines to change this fact. In fact, the amount of power flow between the two areas really depends on the load generation balance and in the two areas. So, you can have a situation where, for example, this load becomes 1200. If the load increases to 1200 and let us say because it increases your frequency will fall. Now, since these areas are connected by AC lines, the center of inertia of the entire system will start falling and you will find the governors here as well as here, if they are enabled, will react and increase their power, and if that happens this power flow could get altered. Okay. But eventually remember that finally when equilibrium is reached, finally the flow in the AC transmission lines which are shown here in these tie lines, let us say, is P1 plus P2 is going to be equal to the load generation balance at the two ends, and this is really depicted in the slide which is shown here. So, you will in fact have the important thing is the frequency at both ends is the same always in steady state of course, and if you are stable, and P generator 1 minus P generator load 2 is the load generation imbalance at this end minus the load generation imbalance at that end. If you assume that the system is lossless, then P1 plus P2 will be equal to the difference between them. So, this is what is seen in a synchronous link. But if you have got a system like this, the frequency of the two regions need not be the same. In fact, the frequency of area 1 depends on the load frequency and the governor characteristics in that area as well as the load and generation balance at a given point of time. And load and generation of course has to be balanced in steady state in this area and this area independently. So, the load here has to be equal to the generation in steady state, the load here has to be equal to the generation in steady state. Of course, there are losses also, and in case there is a load generation balance, the governors will have to respond and the loads also may change their power depending on the nature of the load and the frequency dependence, and eventually an equilibrium is reached when there is a load generation balance. Okay. The flow through this can be regulated, it could be modulated, it could be changed, but in fact if you keep it a constant, then you will find in fact that you can keep it a constant. So, this system in some sense is shielded from changes which are occurring in this system. Okay. So, that is one of the advantages which you have. Of course, the DC link should be used creatively in the sense that if one region does require some help, it should provide it. It can possibly provide it provided this region is able to help. Okay. So, you can increase this power P2, but this is locally determined and P2 is regulated. So, this is effectively regulated. Now, frequency of area 1 and area 2 need not be the same and everything will be normal. I mean, what I mean to say is you can operate this way and operate happily in this way. Yeah. If you have got of course an embedded DC link in a AC system, like for example, in this situation the DC link is in parallel with an AC link, then of course we are back to square one. This is in fact a synchronous link, it is not a synchronous link, because this HVDC link gets embedded in the AC system, there are AC transmission paths connecting these two systems. So, you can't have the frequency of one end different from the frequency from the other. If that were the case, you will have power fluctuations and voltage fluctuations and torque fluctuations in the machine, which is not acceptable. Effectively, you can't operate with the two frequencies being different in this situation. So, the moment you have got an AC line parallel with the DC line, you have effectively made it a synchronous system, and frequency of the area 1 and 2 are the same. Now, the important thing is, of course, P1 plus P2 again will be determined by the load generation difference here minus the load generation difference here. Okay. So, as before, the only change which you can think of here is that this P2 can be controlled. For example, if the total power flow P1 plus P2 as in the example which I had given some time back, P1 plus P2 becomes 500 megawatt, is 500 megawatt. You could make this 250 megawatt and then 250 megawatt will flow to the AC line, but in case I make this 300 megawatt, the flow here will become 200 megawatt. So, you can actually change the sharing of power, but once you have got a synchronous grid, the frequencies at both ends are the same, and the power flow P1 plus P2 in fact is determined by the load generation balance on both sides of the system. Okay. So, that is one important thing. The HVDC link here unfortunately or fortunately cannot do anything to as far as controlling P1 plus P2, but it can control P2. Okay. So, it can in fact alleviate an overload in the parallel line, it could modulate power flow. In fact, you will have swings between the generators and on the synchronous generators on this side and on this side. Okay. So, this kind of thing can happen in this situation. Yeah. In fact, if you connect what are known as fax devices, we have seen some of the fax devices like STATCOM, a static shunt compensator. You also can have series compensators, series capacitors, which in fact are controllable using thyristor controlled reactors, a kind of device which we have considered in one of our earlier lectures. In such a case, you have got a variable reactance device whose effective fundamental frequency reactance can be controlled by controlling effectively the on time of these thyristors. In such a case, you can control X and therefore control P2. But again P1 plus P2, this is still a synchronous grid, and you can in fact P1 plus P2 itself cannot be controlled, P1 plus P2 cannot be controlled, but P2 can be controlled locally by varying the reactance of this. So, the sharing of power in fact can be controlled by varying the reactance of a series connected controllable device. This controllable device here is also called a thyristor controlled series compensator. Okay. In fact, it is a capacitor in parallel with a controllable reactor. So, the parallel combination of this controlled reactor and the capacitor gives you effectively a variable capacitance, okay, capacitive reactance at fundamental frequency. Yeah. If you look at the way our country was, the structure of the power system in our country, long ago, many years ago, before 1991, our grid was in fact made out of 5 regional grids and 5 frequencies. They were different grids and they were in fact operating independently as synchronous grids. Although the nominal frequency of each of those grids was in fact 50 hertz, they were actually operating independently. So, the frequency need not have been 50 hertz, it depends on the load generation balance and load frequency characteristics and governor characteristics in both regions. But the frequencies are more or less at 50 hertz for all these systems, but they were not equal to 50 hertz at any given time. They need not have been exactly 50 hertz, but they were not also connected by any AC transmission path. So, the southern region was not connected to the western region by any AC transmission path, and therefore, it was effectively operating asynchronously. In fact, the northern and the western, and at some point of time the western and the southern region, eastern and the southern region were in fact connected, western and southern region were connected by short HVDC links. and we did have asynchronous connections. So, we did have asynchronous connections between these synchronous grids, but the Indian grid as a whole was not a synchronous grid, but we had small independent synchronous grids connected by DC power lines. Remember that HVDC links can be used to form asynchronous links, but here the DC link in fact does not form the asynchronous link. Then why do you have an HVDC link embedded in an AC system? The reason is of course for long distance power flow, sometimes HVDC is preferable to AC lines, and this is something which we tried to we discussed in our lectures on transmission lines. Okay. So, you can have HVDC links embedded in AC links as well. In fact, even at this time around 1991 or 90 around this time, we did have HVDC links in the northern grid and in the western grid around in the late 1990s. We did have HVDC links both in the western grid between Chandrapur and Padghe within the western grid. It was an embedded long distance HVDC link. We also had embedded long distance HVDC links in the northern region. We also had asynchronous links connecting the western region to the northern region, and eventually we also had asynchronous links connecting the western region to the southern region, and asynchronous links connecting the eastern region to the southern region. So, you had asynchronous links between the region, and you also have long distance links, embedded long distance links within the regions. So, that was how the system was around 1991 to 2000, and after 2003 in fact the western and the eastern and northeastern grids were synchronized by connecting AC transmission lines between Raipur and Rourkela, which is in the central region of the country. Once you connected AC lines, the systems became synchronized. Eventually, even the northern grid was merged with the central grid by connecting the two grids by AC lines, and once you connected them by AC lines, even the asynchronous links which were initially connecting the two regions became effectively embedded HVDC links in the synchronous grid. And in 2014, the southern region was synchronized to the rest of the country. So, now the entire country is in fact operating as a synchronous grid. Yeah. Whether to operate as a synchronous grid or asynchronous grid is essentially a techno-economic decision. There are certain advantages of being asynchronous, operating two grids asynchronously, that is the two systems can be operated effectively independently without one region having to coordinate its generators and governors with the other system, because the frequencies in fact can be different. Then you also have if you have got asynchronous links, you can regulate the power flow between two regions. So, that is much more control over the power flow to through the asynchronous link is there. So, these are kind of advantages of the asynchronous links. If the disturbances on one side, they do not propagate that easily onto the other side. Of course, the disturbance may affect the HVDC link itself, but if the disturbance is relatively far away from the HVDC link, the effect of the disturbance on one side does not propagate to the other. So, there are certain advantages of asynchronous links, but the main disadvantage of an asynchronous link is of course the cost of an asynchronous link. The HVDC converters can be quite costly, and to allow for more power flow, you will have to in fact have have to change the ratings of the converters. AC transmission lines are relatively easier, less costly and easier to install, although there may be some, the economics of course has to be looked at very carefully. It cannot be decided in a simple discussion like this. So, this is essentially carried out by the planning authorities whether we need to have a synchronous grid, and in their wisdom they have decided that well, our country needs to be connected synchronously. So, you have got AC line interconnections now connecting every part of the country to the other. Okay. Yeah. Now, one of the interesting things which you can ponder upon is that you know, the typical AC transmission lines are you know, if you look at the country, you will find that you know, if you look at extreme points, they may be separated by distances of 3000 or so kilometers, or possibly even more. So, they are connected by AC transmission paths. So, one of the things which you need to ponder upon is, in our discussion of um, in transmission lines, I did mention that if you you know, or I can refresh your memory, or in fact we can discuss this point again, is that AC transmission paths, typically we do not have AC transmission lines beyond distances of 300 or 400 kilometers, but now we have AC transmission connecting practically every generator to every other generator in the country. So, is that a contradiction? The answer is no, because it is not one point to point AC transmission paths. At various points, we have got a meshed network and many various junctions in which there are generators, voltage control devices which are connected on the way. So, remember that although now the extent of our power system synchronous grid is you know, quite large, and if you look at just the AC transmission paths, they may be thousands of kilometers long. This we do not have an uncompensated, or you know, just a plain point to point path of 4 or 5,000 kilometers, 3 or 4,000 kilometers. The AC transmissions are connected to each other. There are many junctions. In those junctions, you have got generators, loads, compensating devices, and they are all regulating voltage at intermediate points. So, you can in fact have a AC transmission grid where the distance between generators may be of the order of several thousand kilometers, but you do not have one single you know, you do not have point to point AC transmission of that much length, okay? Because there are of course, as I said, junctions at various places, and those junctions, there may be other devices which are regulating voltages. So, you can operate that way, okay? So, it is not true that there are point to point 3000 kilometer AC paths. There are lots of AC transmission lines. So, you can find a path between two generators through AC lines, but it is certainly not true that there is a single uncompensated path between every generator. That is of course not true. There is a meshed transmission network with a lot of junctions in the network. Yeah. So, if you look at the, in fact, the DC, if you look at our system, now it is a synchronous grid. The southern region also now is synchronized to the northern grid. So, this actually this separation is no longer there, it is just indicative here, but it is, there is no the entire grid is one synchronous grid, that is there are AC line paths between every synchronous generator to every other synchronous generator in the country, not point to point links, but you know, several through a meshed AC transmission path. We do have a lot of embedded long distance links, which in fact are used to send large bulk amounts of power from one part of the system to another. Okay. So, this is certainly existing. Now, there are these smaller links here are remnants of the past. These are small asynchronous HVDC links which were present when the system was not synchronized. Now, they are in fact there in the system, they are effectively like controllable devices, but they no longer function as asynchronous links, because they are now parallel AC paths in the system. So, the main you know, now aspect is how do you securely operate and control power system. If you look at you know, the control spectrum, so to speak, you at one end have got protective equipment, that is the equipment protection. Typically, most equipment protection schemes are basically relays and circuit breakers. They operate within a few cycles, or in it's you know, it could be a few 1 or 2 cycle operation could be there of the circuit breakers. The relay itself can usually detect faults and the location of the faults accurately, and if the fault is within the zone, it may trigger a circuit breaker which isolates or removes a faulted component, and that is essentially the what you call the aim of equipment protection. We do have other protective device called surge arresters and spark gaps, etc. Now mostly we have got surge arresters or lightning arresters. These are in fact shunt connected devices. These in fact break down when the voltage exceeds a certain value, and they effectively provide some form of over voltage protection in our system. But these are kind of not controlled or not controlled devices. On the other hand, equipment protection, in fact there is a relay which in fact has a logic which detects faults, and that effectively triggers protective the circuit breaker. The other fast control in the system is in fact through power electronic controls. In fact, all our HVDC links, excitation systems, etc. typically they allow for sub cycle changes in firing angles and the firing of the devices which are there in the converters, and therefore, you find that they act in a fairly short amount of time. Now, on the other hand, you have got what are known as system protection schemes and damping controllers, power swing damping controllers, etc., which operate at a relatively slower scale. When I talk of system protection schemes, it could mean things like our under frequency relays, that is, if the frequency falls very low, you may wish to trip out certain loads so that to restore load generation balance quickly. So, if there is a very large change in frequency, drop in frequency, you could have under frequency load tripping. You could in fact, if there is a large increase in the frequency, you could even trip generators. You could suddenly when the situation demands change the HVDC power flow. Of course, there could be ramping limits for such devices, but during an emergency you could in fact have a utilize the transient rating of the devices. So, these are called system protection schemes. Also, you have got governors and prime mover controls which are relatively slower, and of course, there is an overlap between all these controls as far as the time of action is concerned, and you also have things like much slower actions like the changing of taps in transformers, and of course, there is of course manual control of ramping up and ramping down the set point of devices. So, these are effectively the kind of controls which exist in our our power system, and if you look at the typical kind of transients which occur, the fastest transients of course the so called electromagnetic transients which occur during lightning and switching operations. This could cause over voltages, but that is usually system is designed to withstand over voltages, or you need to have devices protection, over voltage protection devices like surge arresters. You also have slower oscillations. You could have oscillations between the turbine and the generator, which are also called torsional transients, which are relatively fast. Then you have got the relative rotor angle dynamics, which we in fact saw in a synchronous grid. These are effectively power swings, loss of synchronism, all these are relative rotor angle dynamics. You have got slower frequency dynamics, the center of inertia frequency motion, and of course, in the slowest scale the manual actions, or we can say loads also change slowly, and this is also a transient on the system. But if you look at the aggregate, on an aggregate the loads have a relatively slow change. Okay. So, although an individual load could be changed by switching it on or off, on the whole in a large power system the aggregate load changes are relatively slow. Yeah. And if you look at typical control system, I am not sure how well visible this is on your screen, but essentially you have got a so called energy control center, or there are other words for that. It is also called a system operator, system operator center, or a load dispatch center, which coordinates with neighboring synchronous grids. It prepares the real power schedule, that it tells how much each generator has to generate. Then you can have control the reactive power or control the voltage, that is called reactive power scheduling. You could also control the controllable devices in a network like HVDC, tapped settings of the transformers. This is a part of the network control. One could under certain circumstances have planned load shedding if the shortage exists. So, load also could be a part of the control. In fact, load also in the new scenario could actually take part in controls voluntarily as well. One could in fact conceive having pricing schemes, so that there is some kind of demand side management, so that loads also participate in some way in trying kind of load management, that is ensuring load generation balance. Now, remember that real power scheduling is again effected through the prime mover control systems of the generator, but there are of course closed loop feedback control systems. In fact, for example, generators have got inherent voltage, automatic voltage regulators. You could in fact change the set point of the automatic voltage regulator manually, but once you are given the set point, there is a closed loop feedback, automatic feedback control system which regulates the voltage. Similarly, the governing system is an automatic feedback control system, but you could change the power set point of the prime mover system manually as well. And as we know, in the transmission lines, you have got tap changing transformer, reactive control devices like STATCOMs, static var compensators, thyristor control reactors and so on, which are part in fact of static var compensators and also effect some kind of control. So, this is effectively the kind of leverage or the kind of controls which are there in our hands, which we can use to improve system operation. There are several constraints of system operation. In fact, there are thermal loading limits of transmission lines and transformers, and this depends on the power flows. You could alleviate overloading, thermal overloading. Thermal overloading means essentially your currents are very high and they cause heating in the elements, which could again cause, in the case of transmission lines, it causes sag and eventually a short circuit. If the voltage, the lines sag too much, they may come close to some other devices which are connected to ground or trees and so on. So, thermal loading of transmission lines, there is a limit to that. That depends on how much current is there in the line, which in fact is related to the power flows in the line as well. One could try to alleviate a thermal overloading situation by actually rerouting the power flows from the, if there are overloaded lines and underloaded lines, you can actually reroute the power flow. Rerouting the power flow in a AC system, AC transmission grid is not easy, because you need to change the load generation pattern in order to reroute power flows from overloaded paths. But if you have devices like the TCAC, which I did discuss some time back, or phase shifting transformers, you can actually change the power flow, path of the power flow, or rather reduce the power flow in one path and increase it in another. So, you could in fact use controllable devices like phase shifters or thyristor controlled series compensators to actually change the power flows in various paths. In fact, in the city of Mumbai, which is fed from various various paths from outside the city into the island city. Sometimes in certain corridors you may have overloading, while the other corridor is underloaded, and to avoid that, people are seriously considering some ways of using some power flow power flow control devices. Now, thermal loading of course can be controlled. In fact, you have to reduce the power flow of certain equipment. You can reduce the thermal loading. In fact, I did mention some time back that even a synchronous generator has got a reactive power capability. It has got a MVA capability. There is a field field limit, and that can in fact you know be you if a limit is being violated, you could in fact use the reduce the set point of the automatic voltage regulator, so as to reduce at least the reactive power. So, you can in fact use the controllers, you can have additional augmentations in the control systems, which in case a limit violation is detected, it in fact changes the amount of it kind of changes the set point and reduces the real or reactive power in the machine. In case of an excitation system, if you detect a field voltage limit violation, you will of course reduce the field current, and to do that you actually need to reduce the field voltage, and to do that actually you will have to override some other controllers like the voltage regulator. Okay. Yeah. Power flow controls, as I mentioned, one cannot do it very easily, one has to change the load generation pattern. Rescheduling of generator power is also could be not economical, because different generators have got different cost of generation, and if you actually ask a cheaper generator to back down, you will be actually may suffer economically. So, rescheduling of generator power is a very costly option, which is not usually pursued. Of course, one of the important things in real operation is to actually look at the dynamic line rating of transmission line. That is, remember that the rating of a transmission line depends on ambient parameters like temperature, wind speed, and so on. So, the amount of solar insolation which is there. So, in fact, in winter you can have larger ratings, thermal ratings of transformers and transmission lines, and this could actually be exploited. So, this is one of the ways you could in fact enhance your you could work with smaller margins in winter, so you can, that is one important thing. HVDC and phase shifting transformers, thyristor controlled series compensators is something which I have already discussed. So, we will move ahead. This is something we have also seen before. The sharing of P1 and P2 can be controlled, but remember we cannot control P1 plus P2 if it is a synchronous grid. In AC lines you can in fact again control P2 here with the TCAC, but you can't control P1 plus P2. Yeah. You also have, we have discussed this quite a lot in detail, angular stability problems. You need to have damping of power swings, ensure that the machines remain in synchronism. In fact, the ambient or the steady state power flow in transmission lines also should not be too large, so that the transmission lines give you adequate restorative forces to keep the machines in synchronism. Okay. Now, also saw frequency stability, which is affected by governors and low frequency generation, and of course, there is another interesting phenomenon which is called voltage stability, and we will discuss this now. Consider a system which is of course, before we go there, let us just there are a few other things which I need to discuss with you. Remember that you can improve the damping of power swings by modulating controllable devices in the systems like HVDC, STATCOMs, static var compensators, thyristor controlled series compensators, and also modulate the set point of excitation systems. These devices are known as power swing damping controllers or power system stabilizers. You can improve large disturbance stability by using the transient rating of equipment like exciters, stronger transmission which result in lower transmission reactance, use the transient capability of HVDC under emergency conditions which can quickly increase the HVDC power flow and relieve the power flow on AC transmission paths, parallel AC transmission paths. And of course, in steady state, what we can do is of course maintain adequate margin, that is operate a bit conservatively, so that the system is having more margin to withstand disturbances. Yeah. Now, coming back to what I intended to do, that is the consider voltage stability. Before we go ahead, let us consider what kind of voltage control devices we have. We have got a static, for example, here an excitation system. Here we have shown you a static excitation system of a generator, and you also have devices like tap changing transformers. This is of course the automatic voltage regulator, a kind of typical automatic voltage regulator of a synchronous generator, where voltage is regulated. So, this is used in conjunction with the static excitation or brushless excitation equipment. Now, the other kind of control is using tap changing transformers. Here it is shown schematically. You can actually control the voltage at the load or at the sending end by changing the taps of the transformers. And you also have shunt connected devices like static compensators and shunt reactors, shunt capacitors, switched and fixed, which in fact control the reactive power and indirectly control the voltage of a certain bus. So, you have got all these devices, and here of course, in the diagram I have shown you tap changing transformer. Yeah. Now, one interesting phenomenon which is voltage stability. This voltage stability occurs because of a kind of a selfish load which tries to draw power from a system which is unable to actually cater to the kind of demand which is being made by the load. To understand what I am trying to say, consider a voltage source E which is connected through a transmission system, let us say with source impedances, the transmission system as well as the generating system has got an effective presents to the load, an effective source impedance which is reactive, let us say X, and you connect a resistance to this, let us say it is a resistive load. Okay. So, this is a very simplified model of a system which we are going to study. This load is say a resistive load, and the transmission and the synchronous machine reactance, let us say, is completely reactive. Under these circumstances, if you try to change the load, that is, if I for example reduce the resistance of the load, you will find in fact that the power, as you reduce the load, these values are normalized or per unit values. If you start reducing the load, you will find that the power in fact reducing the resistance, the power increases, and because the resistance reduces, V square by R in fact increases. This is assuming that V is a constant, but V actually also changes, that is the important thing. But initially if you look at it, as you reduce the resistance, power actually increases. So, which is it in fact goes on increasing till you will find that R is equal to X. This is the maximum power point, and thereafter any decrease in resistance in fact decreases the amount of power. Why does that happen? That is because as you decrease the resistance, what happens is the voltage also drops at the load. So, V square by R in fact drops, V square by R increases, the voltage drops, but the reduction in resistance is more. So, what happens is that as you reduce your resistance value, the power still increases, okay? Because although there is a voltage drop, it is not too much, but as R starts becoming equal to X, comes closer to X, a point comes where the drop in the voltage is very precipitous, and V square by R in fact starts reducing, despite the fact that you are reducing R. So, reduction in R does not imply increase in load if you cross this point. So, what does it mean? For example, you have got say a source and which has got a reactance, source reactance of X, which includes the reactance of the transmission path as well as the synchronous machines which are feeding you. and you say connect a bulb, and what you expect is that once you connect the bulb, it will light up. If I want to increase the illumination, I will connect another bulb in parallel, and I expect the illumination to increase. Now, it will in fact increase as you go on increasing the number of bulbs connected to the system, but there will be after a point will be reached when the voltage at the bus where the bulbs are connected falls down so much that any more connection of bulbs in parallel will actually start decreasing thereon the illumination. So, that kind of situation can occur. So, this is what the main point which I want to make here is that if you have got a finite source impedance or a significant source impedance, there will come a point at which connecting more and more loads in parallel, real power loads in parallel will after a point cause enough reduction in the bus voltage so as to cause a kind of counterintuitive behavior, that is, as you add more loads, actually the cumulative power starts reducing. So, this can happen, and this this happens at the maximum power point when this R becomes equal to X. Okay. After that point, any further reduction in R reduces the amount of power. Now, this is in fact what is known as the static PV characteristic of such a system. Now, of course, what will happen is that if you are here, any reduction in R will cause the voltage to drop and also the power to drop. Okay. The voltage drops much more faster after this point. Okay. So, voltage drop and power drop will be experienced at this point once you cross this point. Now, if you have got a controller, okay, if a controller believes you are in this region, and if it is given a command saying that look, I want more power, so please decrease X, decrease R, and it assumes you are here, then what action will it take? It will decrease R, it will increase the power. But suppose you are in this region, if you do the same thing, decreasing the R in fact will cause power to reduce. So, this is a kind of counterintuitive behavior, and if your controller does not know this, he will go on reducing this R, and in fact power will further reduce, and he will go on taking the same action which is wrong in this region to try to increase power. So, if he does not know he is in this region, then he may take exactly the opposite actions and end up reducing the power, and the voltage as well as the power will precipitously fall, and this is in fact called voltage instability. So, how can this occur? For example, suppose this resistance is connected to the system via a tap changing transformer. Let us say A is normal, let us say is a certain value. Okay. Let us say A is 1, let us say. Okay. So, it is a 1:1 transformer. So, the reflected R will be also equal to R on the primary side. Okay. If your tap is changed and the turns on the side of the load increase, in that case the voltage, the resistance which is reflected on the source side is R by A square. So, now what let us try to look at a control system in which if the voltage at the load falls, that is if the voltage on this side falls, you increase A. Okay. So, suppose there is a tap changing control mechanism or control system which increases A the moment you find that the voltage here has dropped below the set point. Of course, tap changing control is slow, but basically if the voltage here at the load falls down, it will increase A. Now, if it increases A, the voltage here will increase provided the reflected resistance R by A square is less than X. If by chance R by A square becomes equal to X, okay. In fact, I am sorry, what I should say is r by a square, as long as it is greater than x, this action in fact will produce the intended effects. But in case r by a square falls below the value of x, what will happen is that the voltage here will start falling at this point, which is also is the same as the voltage here, and any action taken by the tap changer increases A if the voltage here falls. So, any action taken by the tap will worsen the situation. So, this is exactly what I was saying some time ago, that if you are on the, if you are past the point where r by a square is less than x, then any action of the tap to restore this voltage by increasing A will in fact produce exactly the opposite effect that you intend. Okay. So, then the voltage will keep on dropping and the tap will go on increasing, but the voltage will keep on dropping. So, this situation can occur if x is large. So, if x is large, see, normally we do not expect this to happen. Normally r by a square will be much larger than x, but under certain circumstances you can have x becoming very large. For example, a synchronous machine, normally the excitation system would regulate the voltage at its terminals, but in case the terminal voltage is not, one cannot regulate it because the field voltage has reached its limit, that is, the field current has reached its limit because of thermal considerations. Thereafter, this voltage can no longer be regulated because the field current has reached its limit. So, you can't change the field voltage, and therefore, the open circuit voltage of the generator, the internal voltage, cannot be changed. In that case, the series reactance of the generator will start in some ways asserting itself, in the sense that the voltage here is no longer regulated, and effectively the source impedance is going to increase very significantly. So, you can have under certain circumstances the source impedance being very large. In such a situation, r by a square may become equal to x, or may become smaller than x, and any tap changer which tries to increase the voltage by increasing A may actually do exactly the opposite thing of what you intend. What you intend to happen, exactly the opposite thing happens, because you are in now could be in this region. So, remember that a change in the tap, increase in the tap of A effectively reduces the reflected resistance seen on this side. So, in fact, a tap changer action may in fact cause worsening of the situation, that is, every time a tap acts, in spite of increasing the tap ratio, the load voltage decreases because the demanded load power is beyond the capability of the generator and transmission system. That is because the X of the transmission system and the synchronous generator become very large. So, in fact, if you have the transformer operating tap changing mechanism, it will go on increasing the tap, but it will have exactly the opposite effect of reducing the voltage at the load. On the other hand, if you simply disable the tap, you are in a better situation. Okay. So, voltage instability is a dynamical phenomena where the load tries to act in a way contrary and has got unintended effects, because the source impedance at the load becomes very large. Okay. In fact, you may cross so called the voltage stability knee point, and this can happen. Okay. If you are on the other hand having low source impedance, you are effectively, I am sorry, you are effectively in this region, and here whatever control you have will have the intended, the tap changing will have its intended effects. Okay. So, as long as you are here, it is all fine. So, this is effectively voltage instability. Frequency stability and control, remember that the frequency of a synchronous grid depends on the cumulative total load generation balance, and in case a synchronous grid is connected to another system, the asynchronous import also should be treated as if it is a generation. The frequency depends on the load and generator frequency dependence. Generator frequency dependence comes because of governor action. Remember that loads are weakly frequency dependent. Generator power can be made a function of frequency by governor action. And of course, the control of frequency is somewhat hierarchical, in the sense that primary control is in fact achieved by regulating the frequency using governors. The frequency in a multi-machine synchronous grid is regulated by the governor, but not perfectly. In fact, we, as I mentioned some time back, we in fact have droops on the governor, that is, we use proportional control, and that ensures that the sharing of power between various generators is achieved, and droop ensures the sharing of power. Most generators in fact are expected to be on governor control. All these act irrespective of the region they are in. So, governors in fact all generators, most of the generators would be on governor, and in case there is a frequency load generation imbalance anywhere in the system, the frequency of the entire region, if it is a synchronous grid, will drop, and all the governors in the system, irrespective of what part of the system synchronous grid they are in, will act. So, it is a very nice cooperative kind of a federal cooperative structure, you can say. Okay. Remember of course, that once all the generators which are on governor have increased or decreased their power depending on the frequency, the power flows in the areas may change after governing action, and if you wish to restore the power flow between different regions, then you can actually use some kind of secondary control, which could be manually done, or you could have what is known as a feedback controller from the tie lines, AC tie lines, and restore the flow between regions. Remember, synchronous grid, although it is one grid in some ways, same frequency, it may have several regions, and depending on the load generation balance in different regions, the flows could be changing. Okay, depending on if all the governors act, obviously the flows in the transmission network will change. Okay, and you may wish to restore this because regions may actually the power flow between regions may actually be dictated by contractual because of contractual reasons. That is, one region has decided to import or agreed to import or export a certain amount of power. So, you need to regulate that, you may need to regulate that. So, in that case you will apply what is known as secondary control, which is adjusting the generation of various generators, so that you can restore the frequency back. Remember, the droop control does not regulate the frequency perfectly, because it uses proportional type gains or droops, and once all governors have acted, the flows in the system may change, which may be more or less than the contracted value of the exchange between regions, and this you may wish to correct in case you wish to, and this can be done manually or through some feedback controller which takes signals from a tie line. So, this is called tie line control. Okay. Tie line means the line between two regions, not tying the two regions. And of course, after all this has happened, you may still wish to change the schedule of generations and loads, and this may be done to conform to economic objectives like lowest cost and so on. Okay. So, this is called tertiary control. Of course, inadvertently sometimes due to loss of synchronism etc., you may find that a synchronous grid may split up into various regions, and they are disconnected regions, and these are called islands, and now within the island you need to maintain frequency and voltage, and usually the disturbances which cause islanding are quite significant or large impact disturbances, and the frequency and voltage variations may be quite significant, and we may have to rely on additional measures like load tripping, under frequency or under voltage load tripping, to ensure stability of frequency within a disconnected island. So, these are important concepts in the frequency control in synchronous grids. If you want to improve stability, of course, there are several ways of doing it. One of the ways, of course, is during transmission planning itself, you may actually design transmission systems to be strong. That is, they have got good restorative ability as far as keeping machines in synchronism are concerned, under a set of probable discontinuities which may occur. This is of course decided by power system engineers themselves, what are the list of contingencies they ought to consider, like loss of a line for a fault, a 3-phase fault, single line fault with delayed clearing, or loss of a generating station, or loss of an HVDC link. So, these are all contingencies which may be considered during the planning stage, and the transmission system design may be based on that. When you are actually operating, you may actually have what is known as preventive controls, where the operator acts based on some kind of analysis of how the system, how vulnerable the system is, how resilient it is at the present time to disturbances. So, during operation, an operator may actually take control actions, which is called preventive control. You could also have pre-decided or pre-designed automatic high impact discrete control actions, like large load trips or large generation trips, or you can have large changes in HVDC power flow. These may be pre-decided kind of control schemes, which are called emergency control schemes. These are fast acting and are in fact designed to act when the critical event has already occurred and transient is evolving very dangerously. So, these are called emergency control actions. You also have closed loop feedback kind of automatic feedback systems, which are called damping controllers. These are usually pre-designed, and as I mentioned, these effectively are used for improving angular stability of the system. And in fact, if you want to do preventive control, you actually have to have some means of assessing the security of the system. Okay. So, of course, all these controllers are in some sense also overlap, in the sense that some of the damping controllers may be considered as emergency controllers as well, and we shall consider some of these aspects of security assessment in the next lecture.